Hello, it's Arkasha from MCAT Simplified. Today we're going to be discussing pH, pOH, pKw, pKa, pKb, what they mean, the formulas associated with them, their significance, and how to use them. So pH, starting with that, it describes the power of hydrogen, okay? That's what it kind of is supposed to mean. But really, it's referring to the relative acidity of a solution based on the concentration of protons in that solution. And some of the first formulas that you need to know are going to be that pH is given by the negative log of the hydrogen ion concentration in a solution, okay? If you know the hydrogen ion concentration definitively, you can calculate the pH. The H plus ion concentration can also be obtained if you know the pH, because you can take the inverse of this and take 10 to the negative pH, okay? And that will give you this back, the hydrogen ion concentration, okay? Now, also there's the pOH, okay, the pOH, which is the power of the hydroxide ion. And this is going to be given by negative log of the concentration of the hydroxide ion. So again, you need to know this concentration definitively, and then you can calculate the pOH. And then you can get it back, right? If you know the pOH, if you take 10 to the negative pOH, you're going to get the concentration of the hydroxide ion, okay? Now, let's look at this situation. So if we have an aqueous solution, the solvent is water, okay? That's what an aqueous solution basically refers to. If it's at 25 degrees Celsius, the pH scale ranges between 0 and 14. Now, you can still have species or solutions rather that are more acidic than 0, so less than 0, or you can have solutions that have higher pH than 14, right? But generally, the scale is given like this, between 0 and 14. Just keep in mind that this isn't some sort of end all be all, you can have solutions that are higher than 14 or lower than 0. It's just that this is typically how it's talked about. Now, water is amphiprotic. Amphiprotic is a molecule that can basically act as both a Bronsted acid and donate a proton, and it can act as a Bronsted base and accept a proton. So it can do both. It's amphiprotic. Now, if you consider this, and this illustrates this property, this is called the self-ionization of water. If you have a solution of like pure water, for example, you have two water molecules. And notice that I put L, subscript L, suggesting that they're both in the liquid phase. Okay, they are the solvent molecule, effectively. And if they react, this one, for example, it can act as a Bronsted acid and donate one of its protons to the other one. And in that case, one of the water molecules will become the hydronium ion. This is called the hydronium ion, H3O+. And the other, the one that donated its proton acting as a Bronsted acid, will become its conjugate base, which is the hydroxide ion in this case. Okay? So the hydronium, right, this is actually equivalent to a proton, basically. I want you to kind of just think about these as being the same thing. And then there's the hydroxide ion. All right. Now, at 25 degrees Celsius, okay, we can figure out what the equilibrium constant of this reaction is. And that equilibrium constant is referred to as the Kw, okay, which is the ion product of water. Now, for all equilibrium constants, as a reminder, the way you write them is you write the equilibrium constant is equal to the concentrations of the products divided by the concentration of the reactants. And remember, first of all, that with any equilibrium constant, when you're writing it and you're talking about solutions, okay, you can only include the products or the reactants that are in the aqueous phase. You can't include any liquid phase reactants or products, and you can't include any solid reactants or products. So if we write the equilibrium constant for this reaction, which is the K sub W, it's given as K sub W is equal to just the concentration of the hydronium multiplied by the concentration of the hydroxide, because these are the only species in this reaction that are in the aqueous phase, okay? And it so turns out that at 25 degrees Celsius, the Kw of pure water is given as 1 times 10 to the negative 14, okay? Just remember that. 1 times 10 to the negative 14 at 25 degrees Celsius. And if it happens to be pure water, there's nothing else mixed in there. It so happens that when this self-ionization occurs, the hydronium concentration at equilibrium is equal to the hydroxide concentration at equilibrium. So then we can say that if we know the Kw at 25 degrees, which is 1 times 10 to the negative 14, that's equal, based on this equation, to the concentration of hydronium times the concentration of hydroxide. And we know both of these are equal, so we can just say that each one of them is x, so them multiplied would be x squared. And then if we take the square root of that in this side, right, taking the square root of 10 to the negative 14 would be the same thing as dividing negative 14 by 2, okay? Then we're going to get x is equal to 1 times 10 to the negative 7. And so both of these at 25 degrees Celsius in pure water are going to be equal, hydronium and hydroxide, to 1 times 10 to the negative 7. Now, notice that, remember, the pH, you can get it through doing the negative log of the proton concentration, which, remember, is the same thing as the hydronium, okay? And pOH is given by the negative log of the hydroxide concentration. And so the utility of that is usually these concentrations are really small. And so you want to turn them into a number that's more tangible, right? And so doing that, if you take the negative log of like 1 times 10 to the negative 7, that's going to be equal to 7, right? You pull out the negative 7 and then you multiply it by the negative 1 in front, so it turns into 7, all right? So that's much easier to kind of visualize and understand and play with. It's a 7 rather than some, really small number like 10 to the negative 7. So what we can do is we can do the same thing for Kw, because that's a really small number. So we can just apply the negative log formula, the negative log function, to both the Kw and then these two, right, on both sides basically. And so this will turn into negative log of Kw is equal to negative log of the hydronium minus log of the hydroxide, okay? And then we know that the negative log of the hydronium is the same thing as the negative log of the proton. That's equal to pH. And then negative log of OH is going to be pOH. So then we can call the negative log of Kw the pKw. And so pKw is actually equal to pH plus pOH. And that's really useful, because what if, you're asked a question, the pH, it's water at 25 degrees, it's a solution at 25 degrees Celsius, an aqueous solution, water. And the pH, right? And that at that temperature, right, pKw is going to be the negative log of Kw, which happens to be 14, right? You just pull the negative 14, you multiply by negative 1, that's 14. And the pH. So then you can simply calculate the pOH from that, because you're going to do 14 minus the pH and you're going to get the pOH, and vice versa, right? If you can figure out the hydronium ion concentration, you can figure out the pOH, okay? And then you can calculate the pH by subtracting that pOH from pKw. So that's some of the utility of this equation. And here I'm just saying that at 25 degrees Celsius, right, if it's pure water, you're going to have 7 plus 7 is equal to 14. Because negative log of the hydronium at 25 degrees Celsius, it's 1 times 10 to the negative 7, which is 7 if you apply the negative log. And the same thing is true for the negative log of the hydroxide. Okay, that's also going to be 7. So this is going to be pH is equal to 7 plus pOH is equal to 7, which is equal to 14 overall. That's the pKw. But again, you can also just take the negative log of this, and that turns into 14 too. Okay, so what's important is that at 25 degrees Celsius in pure water, it so happens that at a pH of 7, the proton concentration to hydroxide concentration ratio, okay, is equal to 1. So that means that there's equal amounts of protons and hydroxide anions. And so this solution is neutral because you have equal amounts of both, all right? So therefore, if the pH is greater than 7, that means that actually this ratio of proton to hydroxide is less than 1. So there's actually more hydroxide than protons. So this is an alkaline solution, or basic, okay? And then if the pH is less than 7, the proton to hydroxide ratio is going to be greater than 1, so there's more protons than hydroxide relatively. So that's acidic, okay? Now, it so happens, remember, that the equilibrium constant, any equilibrium constant, is going to vary with temperature. And the neutral point of water, right, will also change with changing temperature because it shifts the equilibrium. And so it just happens that if you increase the temperature, right, the neutral point for water will actually start to decrease. Okay, so it'll become it's actually going to be lower at higher temperatures than 25 degrees Celsius. So just to keep that in mind. Okay. So now let's talk about how this can apply when you're talking about a solution with strong acids or strong bases, or weak acids or weak bases dissolved in water. So aqueous solutions of these things. So if we look at the strong acid / strong base situation, right, we got to realize that this whole process of self-ionization is not very significant. It doesn't really happen in very large amounts. So generally speaking, the amount of protons produced, like hydronium produced and hydroxide produced from the self-ionization, in the context of having another acid or base present, that does not contribute very significantly to the overall pH of the solution. So if you have a strong acid or strong base, these species, they're strong because they will completely dissociate, okay, or they will accept all the protons available. So in the case of a strong Bronsted acid, they will completely dissociate to release all the protons they have. None of it will remain in its normal intact form, right? So if you have a strong acid like hydrochloric acid, HCl, and you put it in water, all of that HCl will dissociate to form protons, okay? And that fact, coupled with the fact that really the self-ionization of water is very negligible in that context, the pH of an aqueous solution of strong acid is simply given by the pH is equal to the negative log of the concentration of the strong acid, the starting concentration, whatever you put in there. HA, we're going to say, is the acid, okay? And again, this is simply because, number one, the strong acid completely dissociates, okay? So all of it, the concentration, the initial starting concentration of acid, assuming it only has one proton to donate, will be the end concentration, the total concentration of proton that is released. And at the same time, the self-ionization of water contributes only a negligible amount of protons. So really the overall pH is going to simply be the negative log of the concentration of the strong acid. But again, this only applies if it's a strong acid, okay? And then similarly, if you wanted to calculate the pOH in the context of like a strong base, okay, the pOH is going to be equal simply to the negative log of the concentration of the strong base. Because again, water isn't contributing significantly to the hydroxide ion pool. So really, it all only depends on the strong acid or the strong base concentration. And as an aside, since we're talking about it, here are some important strong acids and strong bases to keep memorized. Because on the MCAT and in your courses, oftentimes you'll be expected to simply recognize when something is a strong acid or a strong base, versus when something is a weak acid or a weak base. So for strong acids, these are some of the ones you're going to see all the time. You're going to have hydrochloric acid, which I just mentioned, hydroiodic acid, hydrobromic acid. So these all have halogens, okay? These are all strong. They readily give up that proton. Then you have sulfuric acid, okay? Now notice this one has 2 protons, but it's only the first proton that is really strongly acidic. The second one is retained more strongly. It's the conjugate base, which can also act as an acid of this species, is a much weaker acid. It isn't considered a strong acid. Only the fully protonated H2SO4 form of sulfuric acid is strong. And then this is perchloric acid, and this is nitric acid, okay? Now, strong bases, right? Generally, strong bases are going to be ones that have alkali metals. It's basically going to be hydroxide ions that are coupled with a counterion in the form of either an alkali metal or an alkaline earth metal, okay? So this is KOH, so potassium hydroxide, lithium hydroxide, right? Those are all both group 1. And then there's this interesting one, which is sodium hydride. So in this case, this actually produces, when it dissolves, the sodium, and then it also produces this ion, which is actually a hydride ion, okay? It's a hydride ion. And this is very, very basic. And then there's calcium hydroxide, so alkaline earth metal, and then barium hydroxide, okay? So again, they're going to dissociate to produce hydroxide. They're going to completely dissociate to produce hydroxide. So those are all strong bases. So those are easier to memorize because you just look for the hydroxides, right? With some sort of metal coupled to it. But then these really do warrant memorization because they come up all the time. and sometimes you're just going to be expected to realize you're dealing with a strong acid, and that's going to affect the pH and the behavior of the solution effectively. And then weak acids and bases. So the thing about weak acids and bases is that they only partially dissociate. So unlike strong acids and strong bases, which form completely to, which dissociate completely to produce either all protons or all hydroxides, these only partially dissociate. So if we imagine a reaction where we put a weak acid, so HA we're going to say is a weak acid in this case, in an aqueous solution where the solvent is water, it's going to react with this water molecule and it's going to form hydronium, right? It donates its proton and it's going to form its conjugate base, which is this, we're going to call it A minus. So if we write the equilibrium constant for this, which we're going to call K sub A, remember that the water isn't included because it's in the liquid phase. So we're gonna say that this is equal to the hydronium concentration or proton concentration multiplied by the concentration of the conjugate base, divided by the initial concentration of the acid. Okay, both of these are in aqueous phase, by the way. So they're included. And so this is going to be the equilibrium constant. And what we can do, right, is because weak acids have a Ka that is very small, right? If we want to make it a tangible number, we can take the negative log of it. Negative log of Ka is equal to pKa. And you're usually going to be given the Kas in the form of the pKa. The pKa is going to tell you effectively, how, basically it's going to be telling you the equilibrium in some ways. It's going to tell you the relative strength of the acid, okay? So the pKa. And notice, right, that the Ka, it's going to be the products over the reactant concentrations. And if the Ka for weak acids is usually really small, it's like negative orders of magnitude. And so that really is suggesting, right, that this is a very small number. It's a very small number because HA doesn't dissociate very appreciably, very strongly. So the reactants are going to predominate. There's going to be a much bigger denominator here than the numerator. So this whole fraction is going to be really small, okay? And again, that's basically saying that at equilibrium, most of the reactant has not reacted. It's just staying there in the same form it was introduced, all right? And that's because this is a weak acid. It doesn't dissociate very strongly. Now, if we do the same thing for the weak bases, right, we're going to say that A minus is a weak base, and it's reacting with, again, the solvent water. And in this case, water will act, being amphiprotic, it's going to act as the acid, and it's going to give its proton to this weak base, which will form its conjugate acid, HA, plus a hydroxide anion, okay, from the water. And again, water is in the liquid form, so we're not going to include it, but if we write the K sub B, which is the equilibrium constant for this reaction with the base accepting a proton, it's going to be the products HA multiplied by the hydroxide ion, divided by the base concentration. And again, Kb is usually really small, okay, because this reaction, this base is weak, so it doesn't really want to react very strongly. So there's going to be much more initial starting reactant than there is product formed at equilibrium, okay? And the pKb is again given by negative log of the Kb. Now, incidentally, if we actually multiply the K and the Kb in these forms, we'll notice that Ka is equal to, hydronium or, proton, however you want to write it, multiplied by the conjugate base divided by HA, and Kb is equal to HA multiplied by the hydroxide concentration divided by A minus. And notice that the HA is going to cancel here and here, and A minus is going to cancel here and here. So you're actually left with just the hydronium concentration times the hydroxide concentration. And remember that that is equal to this ion product of water. And so, therefore, we can say that Kw is also equal to the Ka times the Kb. Okay, and then that also means that if we then do the negative log of all of this, like we did kind of up here, okay, we can say that pKw is equal to pKa, this, plus pKb, this. And again, this is useful because if we're given, if we know it's 25 degrees Celsius and we're given a Ka, given a Kb, we can know that we can divide the Kw by that known value to get the other one. So if we're given the Kb, we want the Ka, we divide the Kw by the Kb to get the Ka. And also, if we know it in the pKa form, it's even easier because we can just do a little subtraction and figure out the unknown value, okay? So again, just take a look at these equations. It's important to have these memorized and kind of know how to use them, because a lot of these situations can arise on the MCAT where you might have to do calculations using this stuff, especially with acids and bases, okay? So just be comfortable remembering these things and remembering relationships between them. And that's our overview of pH-related formulas. Check out our website at mcatsimplified.com.